The broadcast is now starting. All attendees are in listen-only mode.
Hey, good afternoon, everybody, and this is Dr. Mansour, and today is May the 3rd, 2020, and this is our workshop for the Seismic workshop, and let me go to the Seismic course. Here it is. So this is May the 3rd, and this is workshop number 3. Two things very quick before we start. The last semester or the first quarter, as you know, I taught the course the first time based on the new code last semester or last quarter. So the recording is available, and you should have access to the on-demand. So the on-demand of the first quarter, which is about 55 hours, the recording, it should be available to you. Recording should be available for you. It's not for free. You must have a user's name and password. And my staff, they're supposed to send this to you. So you should get access to the 55 hours as an on-demand, which the course I taught on the first quarter based on the new code. If you don't have access, please email me and email my staff, and they will come back to you. They can issue this very quick. I don't know how to do it. They do it for me from home remotely. So info@passpe.com and names@passpe.com also. Those are the two emails, as all of you know. So info and names, email us, and I will follow up with my staff to see if they have any problem, but they can do it from home. If not, they can talk to me over the phone, and I will do it for you from here. But please, you make sure that you have. If you do have a problem with the internet, please let me know when we give you the access to the on-demand. So from any device, as far as I know, you can get access to the recording, and we will keep recording. We keep the recording available for you for 150 days from the day of the first enrollment. But as I mentioned before, more than once, I am really flexible about this to help you guys all the way, because I know the Prometric, they are postponing exams and canceling exams, and they don't know what's going on in this environment, the COVID-19 pandemic crisis, or the unusual situation that we are in right now. I hope that everybody is healthy, and pray for me to stay healthy. I pray for you to stay healthy, and let us take care of our health, and health is number one, and we'll keep working together to achieve our. So this is the first thing that I need to make sure that you are aware of that, and you should have access to the recording of the first quarter. The second thing, as far as this recording here, you'll find that chapter 15 and chapter 16, this was the last lecture I taught last quarter. For some reason, the recording of chapter 15 and chapter 16 corrupted. And my staff, they told me they did everything they can do, even they contact the company that doing this webinar for us. They are hosting it. They tried from their end, and it seemed that the recording is corrupted. Recording is corrupted. That means that we cannot really load it, because if we load it, you will not be able to get access to it because it's corrupted and it is useless. So when my staff or my helpers, they review the recording, they trim it, they took any time that for breaks or any time that at the beginning or at the end, and they try to load only the actual lecture by removing all the recordings that is not really need to be there, like the breaks and so on. So when they did that, they found that chapter 15 and chapter 16, for some reason, the recording is corrupted, and this is why I'm going to do this again this semester. I will teach chapter 15 and chapter 16, and whatever of your choice. I can start today teaching chapter 15 and 16. If you'd like to hold it until next time, I have no problem. So today is the 3rd. I will be glad to teach it again today, chapter 15 and chapter 16. And chapter 15, I sent to all of you the ATC-20, if I'm not mistaken. If you did not receive it, please email me. I will be glad to send it to you, ATC-20. This I send to all of you, ATC-20. And also the chapter, this is, we need it for chapter 15. There is another publication, ATC-20-1. I don't have, I have only one copy for myself, so I don't get it. Which is a field note, which is almost the same as 20, but I prefer if you have both, maybe there is some little bit difference. So ATC-20 and ATC Applied Technology Council. So this already I gave it to you. All what you need to buy ATC-20-1, unless if you like to buy both of them as a package, I have no problem with that. But also chapter 16 of my book is based on chapter 17 of the IBC/CBC. But if you go CBC, chapter 17, not 17A as I talked before, because the California Building Code, they have the A chapters, which we don't deal with A chapters for this course here. Okay, so A chapters are not required. So if you decided to get a copy of chapter 17, which I believe I sent it to all of you also, so please let me know if you are missing any of these. Okay, so those are the two comments I would like to make, just to make sure that all of us who are on the same page as far as the accessibility of the material and the corrupted recording of the two chapters, chapter 15 and chapter 16. So far so good? Okay, so you're supposed to have the two books and the USB, and the USB has this is the textbook, the 16 chapter, sorry, and this is a 626, which is basically all the problems I have in the textbook, and the 300 book. I used to have a book, it's called the 300, and also the practice exams, 2 practice exams. I collect all of them. So this is the maximum number of problems that you will ever see in any package available in the market, as far as I know. So let us do our best. If you can practice all these problems, it will be very, very, very good idea to to practice as many as you can. And okay, I received one question from one of you, our friend here in Fresno. He texted me, and I told him that I will address it. Is a problem 14-4, 14-4, chapter 14 of. He mentioned also about the recording. So I checked with my staff, and they told me that they did I was aware that they have a problem with this chapter, but we were hoping that we might be able to save it or risk it or get benefit from the recording. But they told me no, the recording is corrupted and there is no way to restore the recording. So I have to do it, and I will do it. Okay. So problem 14.4. This is chapter 14. Let's see if there is any typo or any mistake or any disagreement. Problem 14.4 is the last page of this chapter. Problem 14.4. I hope that all of you with me right now. It is this is a textbook on page 452. Saying that a building is assigned a seismic design category F and has a height of 250. Which of the following structural systems would you recommend? So we have seismic design category F, which is the worst. SDC, the height of the building is 250. And he is giving us these choices as far as which structural system should be selected. So the way we answer these type of questions is to go to the source, which is the table 12.2-1, the biggest table available in the code. And we will look to all the options that they gave and see what are the limits. If there is no limit, they say NL. If it's not permitted, they call it NP. So there are two letters they are using. This is the sample problem. Sample problem. 14-4 on page 452 text. So they are using the NP as for not permitted and NL for no limit. And if there is a limit for the height, for example, 160 feet, they will say those are the height limitation, okay, or limitations. But I need to pay your attention to exceptions because they might ask you. So in chapter 6, let me take you to chapter 6, please. And before we hit the table 12.2-1, there is a discussion about like exceptions for the limits for the heights, and we need to be aware of that because this might be a target for a question. Let me locate the section first, and we'll talk about this during the class when I taught the class. Here it is. It is on page 181, textbook. So if you go to page 181, I need to be, this is under figure 6.8, please. So I need you to pay attention to this section because this section is related to the height limits. And the table 12.2-1, the one we are going to look at shortly, gives the height limits for the structure systems and the 6 design categories, SDC. In fact, they excluded the seismic category A. You will not find A over there, so they give you B, C, D, E, and F. The reason probably I mentioned 6 because anything can be built in seismic categories A. SDCA, this is the safest place that where no restrictions like the others, like the other seismic design category SDC. So probably I mentioned 6 because I included A, but the table itself, it does have 5. 1, 2, 3, 4, 5. You'll find that the table has only 5 listed. Sometimes I make a note. For example, if you go to the previous page, you'll find this what I meant. This is here. So the code itself gave only B, but I added A here because whatever is applicable to uh, A is the safest one, so it should be automatically applicable um, um, to A. Okay, so if there is any restrictions, but we can stick with what is given in the code is exactly the 5 seismic category. I have no problem with that. Uh, uh, NL, because as I told you that I have never heard that he will ask you about A, but I included the A in the table just in case. But the questions most likely will be related to these 5 seismic design categories, B and C and D and E and F. The NP and NL, they mentioned here, no limit, NP not permitted. And this section here of the ASCE 7, it is like an exception. Exception in what sense? That we can increase. He said that increase structural height for steel eccentrically braced frames, steel special concentrically braced frames, steel buckling restrained braced frames, steel plate shear walls, and special reinforced concrete shear walls. So they are saying that the height H sub n given in the table are permitted to increase from 160 to 240 for structures assigned to seismic D or E, and from 100 to 160 for seismic F, provided that the seismic force resisting systems are limited to steel concentric braced frame, steel, and they mentioned all them again. Okay, but all this system and both of the following requirements are met. It must be both. The word both is very important, as we talked on the class. They put the word which of the following, or both, or all of the above. Here they are saying that if so, we are allowed to increase the height from the limits given in the table 12.2-1 for these structures only, for these structure systems only, please. Okay, as long as we have met these 2 requirements. Number 1, structure shall not have an extreme torsional irregularity, which is a type 1B. We have type 1A and type 1B. Type 1A is torsional irregularity, and type 1B is called extreme torsion irregularity. The 0.7 and 0.6. I will remind you. I will take you. So this is the first. The structure shall not mean that any structure, okay, that has type 1B, we cannot increase the height. But if the structure in one of these structure systems does not have 1B and is meeting number 2, in this case also, we can increase the height. Okay, the steel eccentric braced frame, special eccentric braced frame, steel buckling, cast in place. Okay, shall resist no more than 60% of the total seismic force in each direction, neglecting accidental torsion effect. Again, this must be given to you. To calculate it on the exam, I believe it will be very difficult. It will tell you that the system is resisting up to 60% or 55% or 50%. So system resists no more. So this is less than or equal 60% of the total seismic force of V. Okay, so these systems that they mentioned, they should not resist. So both, the word both is very, very important. So far so good. This is just worth to mention this before we go to the table. The table right now, we are talking about the table. I prepared it for you. It is a little bit different from the original document, which you have it. And here it is. This is a table 12. So if you go to the text under item number 10 of the road map, if you remember, I have a road map, and specifically on page 209, you'll find that I kept the B, C, D, E, and F. Those are the five, sorry. And this is the structural system limitations, including structural height, H sub n in feet. So if we go to the problem that is given in chapter 14 and see what he is asking, and see if you agree with my selection or not, or to clarify or correct anything that need to be correct. So I'm reading the problem again from another book here. Here it is. So it is 250 feet, just to make sure that. So the height H sub n is given to be 250 feet. And this is a seismic design category F. And he says steel special moment frame. So I will go to, this is a category C, because as you know, this table 12.2-1, it has entries A and B and C and D and E and E, F, G, H. Okay, so A is a bearing wall systems, and they have to give you the system, okay? And category B, building frame systems. And C is the moment resisting frame systems. So the first option of the problem for team 4 is telling you a steel special moment frame. Steel special moment frame. Okay, so steel special moment frame. And this is F, which is the last column here. So I will go, it says no limit. So this one, I can use it for 250. So this is, the answer is A is correct. Okay. The second one, it is a steel special concentric breast frame. Steel special concentric breast frame. And it should match exactly. Steel concentric, okay. This is moment frame system. This is a moment resisting frames. So the building frame system is given on the previous category, which is the building frame system. So since it is concentric or eccentric, it will be under here. Okay, the other one is moment. Okay. So, and I will explain this shortly. So the second answer here is the steel special concentric breast frame. So steel ordinary, I need a steel special concentric breast frame. If you are faster than me, please let me know which entry. Okay, we're supposed to, they number them here. Steel internally concentrically braced frame. This is special steel concentrically braced frame. Here it is, number 2. So special steel concentrically braced frame. Do you agree with me that number 2 is the selection? And I will go here and I will go to F. I found that it is 100 feet under F. Special steel concentric braced frame. Steel special concentric braced frame. So this answer B as in boy is not good because I am limited here to 100 feet. And my building is said 250 feet. So let us go to option C. Special reinforced concrete moment frame. This is category C or group C. So special reinforced concrete moment resisting frame. So ordinary. So special steel special. Okay, intermediate. Special reinforced concrete moment frame. Special reinforced concrete moment frame. So this is item number 5. Item number 5, I will go horizontally. I found this is NL. So the answer C is NL. So I will say this is NL and this is NL. No limit. Okay, and after that he gave us an answer for both A and C, which is answer D, and I selected answer D. Do you see any problem or any discrepancy in my solution here? Do you agree that this is right? Okay, good. Okay, my friend, I believe he is here today. Let me see if the question that came from him. Please let me know, my friend, if you are satisfied with this explanation or you are still having I don't see. I think I told him I will explain this in the class. At least everybody will get the benefit. At least if there is any typo or error in the I don't see him today here unless he's under another name, maybe. Please let me know. Okay, good. Okay, please. I think. Okay, there is somebody is telling me something here. Okay, so this is okay. So let us. Okay, our friend Harut is asking a question 111 of the 626. Okay, sure. 111. Okay, but please, you are very welcome to go over it again and let me know if you are uh, having any disagreement. Okay, so number 111 of the 626. 111 problem 111 of the 626 book. See if I have a nice and a clean copy here today with me or not. Let me grab a copy from the back. Yeah, so I found a copy, but it's not bounded yet. But Problem 111, not page 111. So I assume this is a problem 111. Okay. Yeah, this is a problem 111 here. I will give a chance to everybody to read it for those who did not get a chance to I can get closer to the camera here and problem 111. Okay, so we do have a water tank supported by a frame system. So this is a water tank. And the weight is 8 kibs. This is a gravity load. Okay, the weight of the water tank and its content. And normally we assume it to be full. Normally the seismic code, when we look to the seismic dead load W, if you remember seismic load W, when you multiply this by C sub S times W, will give you the base shear. So the code, when they look the seismic dead load W, seismic dead load, always they look to any containers or any vessels to be operating full. The word operating full is very important. Operating full, F-U-L-L, operating full or in full. I saw both of them, but operating full may probably most. Okay, so in addition to this 8 kibs, the gravity load, there is a lateral load. This lateral load F or V, the base shear was found to be 3 kibs. Okay, so he calculated the V for us, or if this is the base shear, V. So this is F, and we have only one level. I would call it F1. And for any one-story building or one level, always the lateral force at the story equals to the base shear. This is the base shear. Base shear. This water tank is supported by what? Symmetrical braced leg. Okay, so he has some kind of frame, and this frame is a crossing like that, cross bracing, and there is some kind of footing here and a footing here. So this is an elevation. Elevation, okay, you look from the side. There are 3 views, as you know. We look to the elevation, which is like side view, and we look to the plan, which is a top view. You are looking from the top. So side view, like when we look to the irregularities. A plan view, this is a top view, like walls. Okay, when we look to the top views for any floor of any building, and we say, oh, I have a wall here, I have another wall here, and I have another wall here, and so on. Maybe another wall here. So here we are talking about top view. This is top view, looking from the top. This is elevation side view. Okay, and the third one that we deal with is a cross section. A cross section. If he would like to show you specifically certain features that cannot be seen from the plan or elevation, from the plan view or the elevation, normally we come and cut a section like that, section 1-1, for example, and we look to this section, look to the building or the facility after we cut it, and this will give you a cross section. And I will show you that also for one problem that the cross section will able to help us to find out where is the parapet wall. So I needed to be aware of that. These are, and the third one, the fourth one, which normally we don't provide, is the 3D view. So if you look to this problem from the 3D view, you will find the following. You will find that, let me go to, so problem 111 of the 626. So if you look to the 3D view, this is a water tank, and this water tank is supported by a frame, and the frame is supported by some kind of footing. At each corner. I should use different color for the frame, at least to show you the difference. And the frame is braced. Provide a bracing like this. And on the back also we have a bracing like this. Okay, so this is, so we are looking this way. We look to the frame this way. So you see the bracing and you see the water tank. So this what you see is the elevation or the side view. So in this case, the cross bracing is provided on all four sides. So you see, so in this case, we can increase the bracing, but it will be very, very crowded. I draw it only on two sides. So four sides. So the four sides of the frame is like this. I will draw the frame only without the water tank. And the footing is here. And the footing is here. This is OG. And the footing is here. And on the back, the footing is here. So this is the frame. So oops, let me make this nice. Here it is. So this is the frame, and this is OG like this. So this is the frame that's supporting the water tank. And the cross bracing right now They are providing crossplay of 4 sides. That means this side here it is, and this side here, and on the back side, and on the side here. So it is braced on all 4 sides. Okay, so I know the picture probably okay is 4 sides, and the bracing is assumed to resist axial tension load only, no compression. The water tank is required to maintain water pressure for hospital facility. Hospital facility, okay, in order to get, if you remember the I sub E, okay, I sub E and I sub P. There are 2 I's we dealt with, okay. This here, by the way, by looking to this, given system, is it considered uh, a building structure? STRUST structure, sorry. STRU, here it is. Oh my God, structure, STRU, structure, building structure, or is it non-building structure, or it is a component, non-structure component, or it is a frame, a diaphragm or shear wall. These all the 4 systems that we discussed in the class: building structures, non-building structures, let's add S here, non-building structures, non-structure components, or the diaphragm or shear walls categories. Obviously, it is a self-supporting structure, so it is a non-building structure. This, I will classify this water tank that is self-supporting as a non-building structure. Non-building structure. Okay. And he said that not similar to building, because as you know, non-building structure, there are 2 types: similar to buildings and not similar to buildings. Okay, if they are similar to buildings, we analyze them exactly as, okay, and I will show a picture in just a second about this in chapter 8. Chapter 8 of my book, I will show you. So, sorry, I'm explaining a lot of things. He gave you the SDS and the SD1. He gave you the S1 also. And he said, what is the vertical reaction Q sub E at point A due to the seismic base shear only? So if I have this scenario here, if this is a plan view, the elevation, the side view, not the plan view, of the water tank, and this is the bracing system, and I have a force here. F is equal to 3 kibs, and the height he gave you 2 and 2. So from here to here is 2 feet, 2 feet, and the height of the frame is 4 feet. So there is a vertical reaction at A. He called this is A, the footing A. So when this scenario exists, there will be overturning moment, OTM, trying to overturn this water tank about this point here. So there is a vertical reaction here, A sub Y. So if we some moment about this point here, point O, for example, let me some moment here. Remember, there is another, if this is, you are looking this way, so there is one column here and one column here. If you look at it from this side, there's one column here and one column here. So there are two columns. Okay, so you need to be aware of that. Okay, so when I some moment here, this width here must be given. Is it given or not? Yes, it's given 6 feet. Let me some moment about O. And I will call this is the distance B as in boy. And I call the distance from here to here is H. So if I some moment about O, what I will get? I will get the F. Let me write down the equation. Sigma moment about O equals 0 and the clockwise is positive. This up to me, by the way. I can assume counterclockwise. So A sub Y times the distance B as in boy. This is counterclockwise, so it is negative. A plus F, which is this force here, times H, and this is a clockwise, so it is positive. And he said that only for the seismic force. So I ignore this. You remember that there is an 8 kips coming down. This is the dead load, which is the weight of the water in the tank, plus other weight, probably the weight of the metal itself. So, but he told me don't consider that. And this is equal to 0. If I did that, I will be missing one important thing. That also on the other side, remember, there is another column. So this is A sub Y, and also there is another reaction here because there are two columns. So when this is trying to push, here it is, trying to push the lateral force, the seismic lateral force, trying to push. So is this column and this column. So there are two columns. So I have to add 2 here in order to account for the both columns, So if I'm looking for A sub Y, so A sub Y is equal F times H divided by 2 times B. And a common mistake, and maybe he give you answers to match with the 2 and answer without the 2. So in this case, let us substitute for the values and see if we're getting. So F is given to be 3 kips. H is the height. I'm summing a moment here. So 2 plus 4 is 6 feet. Divided by 2. And B in this case is 6 feet. So this will cancel with this. So this will give you 1.5 kips. So this is the reaction at this column here, and the other column on the other side here, if you'd like to call both of them are A sub Y. Those are compression forces. So if we do have an answer 1.5 or 3, because if you omit 2, you will get 3. If you put the 2, which is a correct, so the answer here is, my answer will be B as in boy, 1.5 kips. And you might say, wait a second, he gave us SDS and SD1, and he gave us the S1, so he gave you the seismic design acceleration for short, and the seismic design acceleration for 1 second, and he gave you the S1, the acceleration for 1 second. And here, as you can see, he added G and G and G, but remember, we don't substitute for the G. So, do you agree with this solution, Harut, or do you have any question, or do you have any concern about the process itself, or what is missing? He gave you a lot of information, but you don't need all this, because already he gave you this one here, the 3 kips. If he did not give me this, I have to go from scratch. Okay? And so far so good? Okay. Unless you disagree, please let me know, or any of you have any concern about the concept of the problem, or the I don't consider if only. Oh, okay. Oh, okay. Yeah, be careful with the wording. Okay. He said that, okay, seismic mixture only. Only. Okay. Okay. Let me add a couple things to this problem. Okay. Number one, I have many things we can add it. I will comment about the word only. Because if you consider the gravity load, this is, as you know, this is the lateral load, lateral seismic load, and it should say that seismic base shear, which is the lateral load, lateral force. This is a gravity load. It is a dead gravity load, by the way, it's dead load. Number one, if the 3 kips is not given, if the force is not given, what should you do? In this case, I have go to chapter 8 of my books, which is based on chapter 15 of the ASCE 7-16. And this is a non-building structure, not similar to building. And I have to determine this using all these parameters here. And this is the process. In fact, he saved a lot of time for you. He saved a lot of time. Or he gave you the problem. So chapter 8, which is based on, the title is Structure Seismic Design Requirements for Non-Building Structures, which is based on chapter 15 of the ASCE 7-16. So you will find that for this is non-building structures not similar to buildings, like tanks, mechanically anchored tank. Okay, this tank, this picture here, yeah, I have it in the text on page 311, because as you know that non-building structures, let me just remind you, non-building structures non-building structures they are classified to be similar to buildings and not similar to buildings. This is one classification. To buildings. Okay. Similar to buildings, they must possess three things: 1, 2, and 3. Okay. And this is also from the code. What are the three things that for a non-building structure to have in order to be treated as similar to buildings? And we design it exactly as, here we go. In my textbook, which is a translation of the code, on page 300, that three criteria for non-building structures similar to buildings. Number one, they are designed and constructed in a manner similar to buildings. Number two, let me get the other print because the other print is much cleaner. I have two prints here. This is why I send you another book, because the printing shop, the first time they didn't do a good job. So I send you another copy, chapter 8. Let me use the nice and the clean copy. The printing came, yeah, here we go. Very crisp, and now here it is. Those are the three. It's still the same page 300. So three criteria. This, the title here is non-building structures similar to buildings. Okay. So they should, number one, designed and constructed in a manner similar to buildings, will respond to strong ground motion in a fashion similar to buildings, and they have the same basic lateral and vertical seismic resisting conforming to one of these given in these two tables here. So those are the three requirements that for any non-building structure in order to be analyzed as non-building structure similar to buildings. Okay, and I gave you some drawings or illustrations. This is the table that we use it, the table 1541, the seismic coefficients for non-building structures similar to buildings. So you have to pick the coefficient from here, the R value and omega sub O and C sub D, and the height, if there is any height question. And on the following page, I translate this into English by doing some kind of illustration. For example, steel storage racks, the one big racks that you see it at Costco, okay, or Home Depot, or Lowe's, all these big racks, steel racks, they are self-supporting. Okay, so this is example. Okay, building frame system, this is also, and moment resisting frame. If they are non-building structures, and this is a following, not similar, they have a table for that, which is table 1542, to bring or to pick up the coefficients. But also I provided you with a lot of drawings. For example, a tank self-supported is a non-building structure, not similar to building. If it is mechanically anchored or self-anchored, the cast in place concrete silos, these things that you see on the freeway, storing grains or storing, and I gave you a lot of examples. Telecommunication towers, monuments or amusement structures, and so on. So I give you a lot of, so if the force that the three kips mentioned in the problem, the F is equal to 3 kips. If it's not given, you have to do the whole process, the whole calculation in order to get F first. To get the base shear, and the base shear obviously will be distributed. I have only one level, so it will act at the centroid, and this is the way we do it. So the two I's, by the way, I mentioned, okay? One is called I sub E and I sub B. These are the importance factors, okay? For non-building structures, similar or not similar, okay, we are using the E, the one I sub E. Let me go to the summary. There is a summary at the beginning of the book. Let me give you the summary of the equations. I hope that all of you, they are familiar right now with the book very well. And the most difficult part during the exam is to locate things quickly. Here it is. This is a summary. I have a summary at the beginning of the book. It does have a summary of the equations. So for non-building structures, we have 3 categories. The one is called rigid, and this is only one equation. And the I sub E is used here, I sub E, which is 0.3 SDS W. W is a seismic dead load, not the wind. W is a seismic dead load. Seismic dead load. And after that, we have, this is a rigid. This is a flexible, by the way, flexible. Flexible, you'll find that the T, the period T is greater than or equal 0.06 seconds. But here for the rigid, the T is less than 0.06 seconds. And normally he will give you the period, or he might ask you to calculate the period as well. Can go over a problem. So these are together. These are flexible here. You will find that they are, one of them is called similar to buildings, and one is called not similar to buildings. If it is similar to buildings, everything we did in chapter 6 for building structures, similar to building structures, it is the same equations. All the equations in chapter 12, 12, 12, 12, 12, 12. To get all these seismic response coefficient and all these fancy equations that we use it and we solve. The only thing that we are obligated to pick it from chapter 15 of the ASCE 7, the 3 parameters, the R and the omega sub O and C sub D. Don't pick it from chapter 12. We have to pick it from this table, the one I showed to you. But if the non-building structure is self-supporting structure, this is a basic definition for non-building structures. But if it is not similar, like the problem we just talked about, it is a tank supported by a frame. Cell towers. If the cell tower is supported by a building, this is a different story. I will mention that. But is a cell tower self-supporting? So it is under this category here. So here, not similar, all the equations except two, these two equations. They are in chapter 15. So the remaining, the equations are in chapter 12, similar to this, the same equations in fact. But when they come to the minimum, they don't like to use the minimum for building structures. They decided to increase the minimum. For example, here is 0.004 SDS, greater than or equal 0.01, they make this 0.03. You see the difference? This is 0.5, they make it 0.8 to be conservative. So they increase the minimum. Well, this is why I call it a new minimum. A new minimum is different from the old minimum. I call this, I don't like call this old, but this is the original minimum. And again, here are the equations. The R and the omega sub O and C sub D must be obtained or must be taken from this table here. Don't go to the table 12.2-1 because you will not find the systems listed over there. Because the big table, table 12.2-1, this is for building structures. So we have to decide the moment that I read a problem and it came to the conclusion that this is a non-building structure. So I have to decide I am here or here or here. The period will be the criteria for me here. If I am rigid or flexible. Flexible, they have a period greater than or equal 0.06 seconds. Rigid, non-building structures, the period is less than 0.06 seconds. And I proceed with this solution. So if the F is not given in the problem we are talking about, in this case, I have to go through the process and calculate F. It will take additional 2 or 3 minutes from you to do it, but we are lucky that he gave you the problem, the same problem that you ignore the word only. So in this case, if he said that what is the vertical reaction at point A, that's it, without, so he gave me the, I have this is 8 kips, and I have here 3 kips, and this is a frame, and this is footing A, for example, and the dimensions are given. We'll keep this as 6 feet, and he said this is 2 feet and this is 4 feet. And he said that the reaction at the footing A or point footing A is most nearly and this is a CG here. So let me give you 22 seconds to do it for me, and let us come up with 4 answers. Answer A, answer B, answer C, answer D. And they are in kips. This is F, and this is the dead load down. And I need the answer to be in kips also. Let me give you 2 minutes. Here it is. If you don't have the book, here is a problem. I just change. This is 4 feet. Here it is. Let me make, and this is 2 feet here. Okay. Let us collect some answers and see if there is anybody can help me with. So this is a water tank here, or the storage, or whatever facility he's talking about. Little tiny change in the problem, the question that any answer, or I don't know the answer. I just made the problem right now. I don't have these questions, but it's a good idea to raise this question right now because it has two important things that you might. Okay, it seems to me that we're getting a number from one of you. That's good news. Let us see if Okay, I got 3.5. I'm not going to mention any name. Any name, okay, just 3.5. So this is one answer from one of you. If you can get, if I get another answer, will be good. I get 7. Okay, I get 7, which is twice of this amount, 7 kips. Okay. Any other answers? Okay, let's do it together and see if we are getting any of these answers. This is 6 kips here. 6 feet, sorry, not 6 kips. Just to make it a little bit bigger. Again, I will call this point O, and I will put my finger here, and I assume that the reaction at A sub y is up. And I will sum moment about O. Sigma moment about O equals 0, and clockwise is positive. As I told you, this is optional. You can assume this. Is up to you. Either this or this. But the moment you assume it, you have to stick with it all the way to the end. Okay, so we used the clockwise last time. Let's use counterclockwise. Let me get rid of this. I'll put my finger here. So I have 3 kips times the moment arm, which is 6, which is 2 plus 4, and this is clockwise, and I assumed so this is negative. I finished this. I found that the 8 kips times the arm, right now, this is 6 feet. We assume that the center of gravity is here, or the centroid for this location. Center of gravity, much better word, centroid for an area. CG, we call it center of gravity. So it is midway, so it is 3 feet. So this from here to here is 3 feet at each end from the centroid. So 8 times 3. And also this is going to be clockwise, so it is minus the A sub y times 6 feet. And since I have 2 of them, so I multiply by 2 columns. And this is counterclockwise according to my, so it is a plus, and this is equal 0. Okay, did I miss anything? So A sub y in this case is equal to, these are, both of them are negative, they can go to the other side. So it is 3 times 6 plus 8 times 3 divided by 2, or 6 feet times 2, 2 columns. So if I did this, you'll find that this is 18 plus 24 divided by 12. So this is 4 and 8 is 2. So it is 32. So it is 42 divided by 12. And if we do this math, 42 divided by 12, let me bring my calculator, even we can do it by hand or from our. So 42, enter, 12 divided is equal to 3.5 kips. Any question about that? This is straightforward moment calculation by taking the moment about a certain point, and we need to master this because this is something very, very important. Let me highlight one thing. And I will go back again to this problem, but based on this, right now, the answer is A, which is 3.5 kips. Don't forget the 2, because this is the 2 columns. Okay, because we said that obviously the same problem we're talking about, that this is, there is another column here. So this force is pushing. So in this case, there is another column here. 2 columns will be compression, and the other 2 columns will be tension. This is compression, but this compression and this compression. They will be under the compression force. I will go back to mention a little bit more about this, just in case, but let me remind you of something. We talked about it in the class. And let me I will use the same values. The 3 kips, the F is equal to 3 kips. And I will use also the 8 kips. And I will call this is also A, but I will call this is B this time. And the distance between these 2 columns, they are also 6 feet. And keep the dimensions as before, 2 feet and 4 feet. And the brace also, I have no problem with the bracing system, the X bracing. But here I will ask the question differently. Okay, we'll say what will be Okay. We'll say that the uplift force at footing B is most nearly, and also another 4 possible. Okay, the uplift force at footing B as in boy, here it is. Just during the break, you can think about it. Let's take a few minutes break. 10 minutes, let's come back after 10 minutes, please. Let me go and wash my face and come back fresh. Okay, and after 10 minutes, we are going to meet again. Okay, thank you. But you are very welcome to keep working if you like to keep working. Thank you. Okay, thank you very much. Okay, waiting. So if we look to this problem here, so we have a gravity dead load and the lateral seismic force, which it came from the base shear that he might ask you to calculate it as part of this problem, or it could be a separate problem. So the base shear V, which as we discussed before the break, this was going to be non-building structure, not similar to building. You have to follow the equations for the non-building structures, not similar to buildings. I received, I believe, an email from one of you. We send you with the two textbooks, a USB. Okay, it does have the 6 to 6 CBT problems. So all the problems based on the new code, the ASA 7-16, IBC 2018, and so on. So when you install the software, it will generate a password. The instructions, by the way, is given also on the same USB. There is a Word document. My staff, they explain to you how to install the software. The computer will generate a password for you. Please write it down, and you have to enter it as the computer will generate it for you, because we have no control over that. Some of you, I received an email asking where is the password. No, the password, we do not generate the password. The computer will generate the password. The programmer made it that way. The programmer I hired to write the program for the CBT exams. There are many commercial school maker and test maker. There are many software available in the market based on the CBT computer-based test format. But in my case, or I started way back and I hired a programmer and he wrote the program, and you don't need to have any software. It's already executed and ready to be installed in your computer, but it will generate a password. Write it down and enter the password as it's given to you exactly, verbatim. After you enter the password, you are a user of the program and you can generate as many exams as you want. It is 55 questions. The computer will grab 55 questions out of 6 to 6 and will give you 2.5 hours to simulate the actual time for the actual exam. And after that, you will get your percentage, how you did, and tells you what was the correct answer and what is the correct answer, what is the wrong answer. And it gives you the problem number, by the way. It gives you what problem in this book, in the 626. So problem number 300, for example, problem 491. If the computer picked a problem 491, he will grade it for you and see if you did it right or wrong. And he will tell you the problem, where it is located in the book. So at least you can go and read the problem one more time. And you can look to my solution that I provided at the end and see if you agree or disagree and what mistake, if any mistake you did it. At least we can learn from our mistakes. So please do your best. If you do have any problem with the CBT that we send it to you, please let me know and we can figure it out to see why the CBT is not working or is not running. But please do this as soon as possible. Don't wait until the exam 2 weeks away and start to use the USB or the CBT exams. No, I need you to install it and start to use it as soon as you can, so we can figure out if there is any problem as early as possible before we come to the closer to the exam and we start to um, look for a problem if there is any. I hope not. Okay, let's go back to the problem. This is just, I remember during the break, I need to mention this statement. Um, just to remind you. So, the uplift force, because of this lateral force, is pushing this water tank to rotate about this point A. So, there will be an uplift force, uplift force, uplift force. Uplift force is a tension force, tension or tensile, tension or tensile force. So if we look to this, you'll find that we do have the I have a reaction here, A sub y, and the reaction here is B sub y. And we draw it down because as this force trying, so, and we'll see if the reaction direction is not clear to you, okay, we can assume a direction if we ended with a positive sign, that means that your assumption is correct. If we ended with a negative, our assumption is wrong. Because maybe this force, the dead load will, so I will, some moment about A. So I will say sigma moment about A equals 0. And again, clockwise or counterclockwise. So if I some moment about A right now, so I have 3 kibs times the moment arm, which is 6, and this is the clockwise, so it is positive, and the 8 is counterclockwise, so it is minus 8 times, again, I will assume that this is the centroid, this is the CG, it is halfway, so it is 3. And I assume B sub y is down, so it's counterclockwise, so it is negative. B sub y times 6 equals 0. So far, so good. Did I miss any? Did I miss any force? This is B sub y. Let me just make it nice and clear here. B sub y. So right now, we can say that B sub y is equal to, I can move this to the other side, and this is 18 minus 24 divided by 6. And you will find that we have a negative number here, so negative 6 divided by 6 is equal negative 1 kib. What does it mean negative? Negative means that my assumption is not correct. I assumed there is an uplift force, but in fact, we are going to end it with a force in the opposite direction. That means that B sub y is equal 1 kip upward is not. So in fact, we don't have any uplift force. We don't have any uplift force here. And maybe he will give you a 0, by the way, as among the answers, because we came negative. That means that uplift means that, if you remember chapter 3 of my book, let me take you to chapter 3 to remind you with the drawing or the illustration when I talk to overturning moment and uplift forces. Coming close, here we go. Let me see, where is the, here it is. It was on the previous page. Here it is. Figure 3-2. If by chance you have the book, that's good. 3-2. This is the uplift force tension. Here it is, tension. So because of these lateral forces, here we don't consider any gravity force. So there is a compression side, which is these forces will try to, the inertia force due to the seismic forces, it's trying to push the building to the right. So if you take moment here, there will be uplift force. This is called uplift. And this is a compression because the building will be like this. So this is a tension side and this is a compression side. On the same page also, if you remember, and this is the second point I would like to make, that when we calculate the resisting moment, because there are two moments, there is a disturbing moment and there is a resisting moment. Okay? So the resisting moment is a moment due to the gravity dead load. We multiply it by 0.9 if the strength design is used, or 0.6 if ASD allowable stress design is used. The code is asking us to reduce the dead load by 60% for the ASD and 90% for the strength design, which is the seismic design philosophy for it. Okay, we are using these. For the seismic design, we are using the strength design, or the seismic force is based on the strength design. So here, this is a dead load. I do not apply any reduction of the dead load. So if I recalculate right now, this is without reduction. And I would like reduction of the dead load. If I reduce the dead load, as the code asks me, and that's why I will do it two ways, and I'll tell you what should you do in the exam. Sigma moment about A plus 3. This is a calculated value, so 3 times 6 minus. Now the dead load. This is 0.9, because this is the strength design, times 8 times 3, and minus B times Y. The code introduced the 0.9 for the strength design, or if you are using the ASD, you have to reduce the dead load by 60%, like a factor of safety, or like a safety factor, additional safety factor. So if you calculate right now, since we are not using the ASD, the allowable stress design, we are using the strength design because the force is given as a seismic force, and the seismic force is based on the strength design. So I have right now B sub Y. Let us see what we are going to get right now. We are going to get 18 minus 0.9 of 24 divided by 6. So the reduction is very, very important. Okay. 0.9 enter 24 times. Okay. And this is 18 minus. So 3.6 minus 3.6 divided by 6. So as you can see, this number is getting smaller than 1. So it is only 0.6 kips. And it is negative. So this without reduction, this is with reduction. I reduce the resisting moment because here we have two moments. Here I have two moments. I can say this problem, I set it up like this using superposition. I can say that this is the water tank by itself. Which it has the 3 kips, plus the same water tank, but I will have only the gravity 8 kips. And this is the end A here, or support A, or footing A and footing B, and this is B and this is A. So here I have two moments. When I sum moment about A, there is a moment due to this force, which is overturning moment, OTM. Some moment here about A, so it is force times distance. Rotation moment, or disturbing moment, or overturning moment. OTM is the best name. This is clockwise, as you can see here. This is a disturbing moment. It's called disturbing moment. The gravity load is going to create another moment, and it's going to be in the opposite direction. This is clockwise, by the way. So if you look, if you sum moment here, you'll find that the moment is like that. This is called resisting moment, RM. Try to prevent the building or the tank, in this case, the water tank, from overturning. It's called RM, the resisting moment. The resisting moment is based on the dead load, which is the total dead load. We take the dead load only, not the life load, because the life load not over or not exist over the building for 24 hours. So the code is allowing only the dead load. If you look to the load combinations, all this, by the way, is shown, and I talked about this in the class, but I'm reminding you, here it is. If you look to the load combinations, strength design, or the LRFD, you will find that whenever we have a seismic force E, they put 1.0, you see, to tell you don't multiply the seismic force by any factor. It is already at the strength design level, so we don't really multiply it by any factor. But for the dead load D, we multiply by 0.9. This for the strength design / LRFD, load and resistance factor design. So if you look to the ASD, the allowable stress design, which is the other philosophy, you will find that also for E, here multiplied by 0.7, and this is a conversion, as you know. Here they are using 1.0 because the earthquake force using the current code E, it is at the strength design level. And that's why when we are using the E in the strength design load combinations, they put 1.0 E. They do that way intentionally. What is 1.0 E? Is E. But why they put 1.0 before it? To tell us don't multiply by a factor because it's already at the strength design level. But when we look to E at ASD level, there are two ways given in the code. It is multiplied by 0.7 0.7 E, or they take E and they divide it by 1.4, which will give you almost the same. 1.4, if you take the inverse of it, it will give you about 0.7. Okay, 1.4 inverse here, it is 0.714, and they round it to be 0.7. And they are happy with that. So either this or this. This is to convert the earthquake force from the strength design to the ASD. So if we are designing a structure based on, or if you are given a problem based on the allowable stress design, ASD stands for allowable stress design. So in this case, you have to do this conversion here. So going back to the problem, as you can see here, this reduction here, 0.9, don't forget it. So with the reduction, which is based per the code, with the reduction of the dead load, and this is the code requirement, okay? Reducing the dead load when we calculate the resisting moment, because like another layer of factor of safety or another factor of safety or another, okay, safety measure they introduce. Even the dead load, when we calculate the dead load, by the way, dead load is very accurately, okay, calculated. But if you remember when we uh, used the load combinations for steel and concrete design, the 1.4 dead plus 1.7 life, they assign only 1.4 for the dead load, but for the life they assign a larger factor, because the dead load is more accurately can be calculated compared to the life load. Life load is, okay, there are many variations, so they increase the life load by 70%, while the dead load by 40%. If we use this equation, okay, there are other equations, okay, but normally, okay, or generally speaking, the factor for the dead load is less than the factor for the life load due to the uncertainty in estimating the life load. Make sense? Okay, good, good, good. All these things are, I hope that uh, are good points so let me open the 626 and uh, just look to a problem in front of us here, problem 352. Okay, problem number 352. If you have the book, that's good. If not, here it is in front of you. This is a plan view, which is a top view, which is good. A plan view. Okay, and we have the one-story masonry shear wall structure with a rigid roof diaphragm. Rigid roof means that we have a torsional moment. The location of the centers of mass and rigidity are given. So the center of mass and the center of rigidity, they are aligned, or they are on the same line of action. So considering the accidental eccentricity, the direction of the torsional moment, accidental eccentricity, there are two E's, E eccentricity, E accidental, and E actual. The accidental eccentricity, can say ACC, sometimes put ACC accidental, or just E sub A. The actual eccentricity is the perpendicular distance between the center of mass and the center of rigidity in the direction of the analysis. In our case, the actual eccentricity for this is what? Is zero. E actual for this one is equal zero because they are the same along the same line. Here it is. Okay? If the center of mass to the right or to the left, or the center of the, so in this case, we will have actual eccentricity. So if you look to this building, let's assume that we have this building here, assuming that it's a plan view. And we do have the center of mass is here. We solved a problem last time about the center of mass. It's very important to know how to calculate the center of mass and the center of rigidity. Please let me know if you have any issue with that. And let's assume that the center of rigidity is somewhere here. We have CM and CR. We agreed that the V, one of the 7 rules, do you remember the 7 rules? V is always acting at the center of mass, always, V. The base shear always at the center of mass, always. So in this case, yes, we do have an actual eccentricity. What's this here? This is the E actual, the actual eccentricity. Is the perpendicular distance between the center of mass and the center of rigidity. But the problem that he gave us here, the center of mass and the center of rigidity, they are along the same line in this direction, by the way. The other direction long, the east-west direction. So in this case, the east-west direction. So there is an eccentricity, which is this distance from here to here. But I'm talking about in the direction shown, which is the north-south direction. Even with zero actual eccentricity, the code is still asking us to consider the what is known accidental eccentricity, the E accidental. Again, another factor of safety, or another safety factor, if you like to call it. So they are saying that the center of mass, center of rigidity will stay as is, does not change. What is really moving is the center of mass. Center of mass, one time we are going to put it this way, and one time we are going to put it this way. We're going to move it 5% of the dimension perpendicular to V this way and 5% this way. So this is 100 feet. So I will move the center of mass to the right here, 5% of 100 feet, which is 5. And I will move it the other direction, which is also 5% of 100 feet, which is 5 feet. And this is why the code is say a plus or minus 5% of the dimension perpendicular to V. L perpendicular to V, which is in this case, this dimension here is the perpendicular to V. So we move the center of mass to the right one time and to the left one time, and we take the most severe condition. So if I move the center of mass to the left, always V will go with it. So the V will be here. So I moved it from its calculated location to here. And I put my finger at the center of rigidity. This V right now, which is shifted to the left 5 feet, as you can see, is going to create what? Counterclockwise moment. Are you following me? If we take the other side, so this is a plus 5%, and this is a minus 5%. And always remind me, by the way, if there is anything I can show to you in the code, I would be glad to show it in the code if there is any. So if we move the V right now to the right to take the 5% positive, the center of rigidity is still the same. So it's going to rotate the entire building around the center of rigidity, which is the center of rotation also, by the way. You will find that there is a moment clockwise. So I have, if we move the center of mass to the left, we'll create counterclockwise, clockwise. This is why CW and CCW counterclockwise. So he didn't tell me anything other than what's given. So I apply the code. So in this case, it could be either clockwise or counterclockwise. This is why the answer is D as in David for a problem 352. Any question about that? Agree or disagree? I know there are some questions that are a little bit tough or vague or not clear. Make sense? And I'll be glad to go over torsional moment equations and torsional moment calculations. I know I covered it more than once, and during the semester, the regular semester, the first quarter, we solve many problems. Don't forget to subtract the negative torsional shear. Negative torsional shear should be subtracted, not to be ignored. Negative torsional shear should be subtracted. Don't ignore it, as some books mention that for the sake of the exam, you have to subtract the negative torsional shear. Don't ignore it. Yes, in your own private business, if you like to ignore it, that's fine. You are on the safe side. Or you are on the safe side, okay, if you ignore it. But for the sake of the exam, I will subtract it, okay? And so don't forget that the center of mass is the one is moving, not the center of rigidity. Because the code allows us to move the center of mass plus or minus 5% of the dimension perpendicular to V. In this case, this is 100 feet, so it is, I can move the center of mass from its calculated position or calculated location. Good. Since we are on the same page, problem 353. The vertical distribution of seismic forces bear the simplified procedure. Simplified procedure, this is the alternate design method, bear section 12, 14, chapter 12, 14 of the ASCE 7-16, they came up with another method other than the ELF and the dynamic. They call it simplified, or sometimes we call it alternate design method. Alternate design method. So, is not directly a function of is not. Be careful. Is not directly the distribution, by the way, vertical distribution. Okay. After we calculate the base shear, as all of you know, so there are 3 steps. If you have a building structure like this, I'm using a straight edge to avoid this slabby lines. Here we go. But anyhow, so after you calculate the base shear, which is the first step, using whatever method is C sub S times W for the ELF or ELF, equivalent lateral force procedure, uppercase, much better. After this, we distribute the force among the levels, and we call this is F1, and this is F2, and this is F3, and this is F4. So there are 4 forces, one at each level. And we calculated this way based on Fx is equal C sub Vx times V. Do you remember this equation? This is called vertical distribution factor. Vertical distribution factor. C sub Vx. So this is the first step, as you remember, and this is the second step. We cannot do this until I calculate the base shear, because the base shear is required for the distribution. And why do we do the distribution? Why we do this step? In order to get what is known as a story shear. Story shear is, this is V4, and this is V3, and this is V2, and this is V1. Bear this equation, by the way, this V is given by the code. V is equal the sum of the Fi from I is equal X to N, not from 1. This equation is very important. This is the second equation in the code for the section that we are covering from the code. Let me make sure that the counter started from X, not started from 1. So, for example, what is V4 in this case? V4 is equal F4 only. That's it. Because the X is at the 4th level. As I go down, this is F3 plus F4. And V2 is equal F2 plus F3 plus F4. And V1 is equal all of them F1 plus F2 plus F3 plus F4. So we do this distribution to calculate these F's, the force at each level, to get what's known, these we call them story shear. Story shear. At each, this is story 1 because as you know, story is a space between levels. So this is the story 1, and this is the story 2, and this is the story 3, and this is the story 4. 4 stories. At each story, we calculate the story shear. To use it, we use this to design shear walls. These forces will be used to design shear walls. Makes sense. Okay, so the distribution, this is called distribution. Distribution is done by three methods. The distribution of the base is called distribution of the base shear, V. One is the dynamic, which we are not going to cover it because we don't do it here. Dynamic analysis to get the Vs, but which is basically force is equal mass times acceleration. But the distribution, no. The second method is the ELF, which is F sub x is equal C sub Vx times V, the equation I just wrote right now. The third method is for the simplified method, which is the third method, because as you know, there are three methods of analysis in the current code. Oops, this is 2 and this 3, not 4. So the simplified, the distribution, they don't use this equation. They came up with a very simple one. It's called F sub x is equal lowercase wx over w times v. Again, all these equations are given in the code or in my books. I can show to you exactly where is the equation. If you have doubt, you want me to show this equation? This is in the textbook. Let me bring my textbook. In chapter 6, under the section of 1214, let's go to chapter 6 to show it to you. And also it will be a good idea because sometimes I forget equations. I'm getting old and the memory is not as fresh, you guys. Here it is. This is the equation 12, 14, 13. F sub x is equal W sub x divided by W times V. This is on page 238. It's called vertical distribution. The force at each level shall be calculated using the following equation. And the equation I wrote before to get this, here it is. This is for the story shear. The design story shear is given by this equation. V sub x is equal to the sum of the Fi, where I from x. You see, I from x. This is equation also given in the code. ESE 7-16. But he's not asking for this. He's asking for the distribution, which is, so going back to the original question, sorry, I'm taking you back and forth, but I needed to understand, and you should, whatever material you are using, I hope that you are prepared yourself to a degree that you know exactly where every equation, every table, every chart, what time is the biggest enemy for you during the exam. So if you know exactly where are the things are located, it will be very good. So let's go back again to the question 354 of the 6 to 6. Which of the following, okay, the vertical distribution of the seismic forces, seismic forces or seismic force, it could be a plural, it could be, where the simplified procedure is not, pay attention to that, keywords, some keywords, it can help you a lot to figure out. Period of the structure, T, the height of the structure above the base, which is H sub n, the effective seismic weight of the structure, which is W, or the answer D, A and B? The equation I just wrote, which is f sub x, is equal W sub x divided by W times V. This is the equation that we use for distribution. T is not part of the equation, so this is yes, this is not. The H sub n also is not there. The effective weight, effective seismic potential, no, it is here. So these two elements are not. So the answer D is the best answer. Agree or disagree? Be careful with the wording. What is meant by that? What is, oh, this is very easy. Let us look to this, which is part of chapter 15, by the way. A problem is 341. And let me give you a chance to read it. This is a pipe, a utility pipe, water line. It is above ground, and it is subjected to a left lateral strike slip fault. If the and I will give you 22 seconds. Let me make the zoom a little bit much better. Okay, let me, not 22 seconds. What about 2 minutes? For those who do not have the problem. Oh, sorry, here it is. Okay. I will explain it to you, and I hope that this will help you to answer any question related to this topic, because sometimes it's a little bit confusing. But bending stress or flexure stress, this is the type of the stress that it has tension plus compression at the same time. So I need you to know that the bending stress or the flexure stress is a type of stress that occur, and it will cause tension and compression at the same time, simultaneously. Okay, they are happening together. Like like this here. So bending stress or flexure stress, bending or flexure stress, slash bending. Like you have a beam, cantilever beam or a simply supported beam, any kind of beam. And this beam is subject to a load, a distributed load or a concentrated load or both. So this beam is expected to come down like this. This is a deflected shape of the beam. So we have one side is tension and one side is compression. This is a tension and this is compression. This is why if this beam has a cross section like this, assuming this is a concrete beam, where the rebars should go, the rebars should go along the tension side. And we put the strip, okay, the vertical for shear reinforcement like that. But the main reinforcement is supposed to be at the top, along the tension side, because concrete, as all of you know, is very strong in compression and very weak in tension. So this is called bending stress or flexure stress, where the tension plus compression happening together simultaneously at the same time. Always, I need you to remember this. In our scenario here, this water line, here, it is above ground and it is subjected to above ground an area where it's having left lateral strike force. Left lateral means that if I'm standing here on this side of the fault, where is the fault, by the way? Here is the fault. This is the fault. The fault line is here. And the fault is having a small angle, acute angle, about 15 degrees, 20 degrees, something like that. And this fault is the left, mean that if I'm standing here, the arrow has to go to my left. If I'm standing from here, the arrow will go to my left. This is called left lateral fault. So if you have a fault, this is a fault line. If this fault is left, mean that if you are standing here on this side of the fault, the arrow should go to your left. If you are standing here, the arrow should go to your left. This is called left lateral fault. If we do have another fault, but it is right, this is a fault line, and it is, instead of left, it is right. So if I'm standing here on the side of this fault, the fault should move to my right. If I'm standing here, the fault should move to my right. We need to know that. So this is called left lateral fault or left lateral strike fault. I have no problem with that. Slip fault or the right lateral slip fault. Okay, strike slip could be added to it. This is something that I needed to remember. I know you remember this from geology class or probably from the seismic class. The other thing I need you to remember, because this will help you to understand if the fault will cause tension or compression, a force, if there is a force like this force could be resolved into two components. One in the x direction, we call it F sub x, and one in the y direction, we call it F sub y. And if we know this angle theta, as you recall from statics, F sub x is equal F cosine theta, and F sub y is equal F sine theta. So far, so good. This is static, resolving force or resolve forces or resolving a force. We are going to apply something, okay, similar to resolving the forces. Let's look to this. This is left lateral. That means that if I'm here, it is left. So this is arrow like this. And if I'm here, so he showed two arrows. I have no problem with that. So the actual drawing is the left lateral. But if you look, if the same above ground lifeline, but the active fault is the right lateral fault. So he's giving you a drawing for left and asking you for a question of the right. Be careful about that. This is very common, unfortunately, because you might look to the picture and you do the analysis based on the picture, or you do your answers, or you select the answer based on the picture given. This, as is given like that, it is left lateral strike slip fault, left. But if we look to the right, I will draw a pipe here somewhere, and here is a fault line at a small angle or so. And right now I need it to be what? I need it to be right. So if I'm standing here, the arrow will be to my right. If I'm standing here, the arrow will be to my right. If you'd like to draw another arrow here, I have no problem with that. Here it is. If you'd like to draw another arrow here it is. It is opposite. This is right. And this where the answer should be based on, not this. Are you following me? So for faults can cause tension, stress or tensile stress. It can cause compressive stress. It can cause shear stress, but it will never cause bending stress. So bending stress is out. So I needed to remember that. So at least I can narrow my choices. And instead of answer, for answers, I get rid of one, because seismic faults or faults movement will not create tension and compression at the same time. Either the pipe will be under tension, or the pipe under compression, or will be under shear stress. I needed to remember this fact. So this is out. So I have, instead of 25%, I have 33% now. Because at least if I have only 1 minute left and I can remember and I have no time to look to any reference with me, but at least by the process of elimination, if you can eliminate one answer, so it is 33% instead of 25%, much better. And I will select one and pray to God. If I have only 30 seconds left and they're telling you, okay, 1 minute left or 30 seconds left, and you need to punch your answer or push the button or push the keyboard, at least 33% better than 25%. But we need to do it right. So if you look to this drawing here, and let me do it here. If this is a fault, and this is a pipe, sorry, my fault is a little bit different, but and the fault is still right, lateral fault. I draw it again at least. So if I'm standing here, it is my right, and if I'm standing here, it's to my right. Draw only 2 instead of 4 to make it easy. So this is still right, which is the same as this one here. So if you look to this is a movement, which is a force along the fault. This can be broken down to 2 components. Let me select different color here. So this force here, if you remember the force resolving forces, it will be 1 in this direction and 1 in this direction. And I get rid of this. So again, this here, it is 1 in this direction and 1 in this direction along the pipe. So I get rid of this. So if you look, these 2 forces, they are pulling the pipe. They are pulling the pipe. They are pulling the pipe. Okay, this and this. If the same lifeline, but it is the right lateral instead of left, just to make sure that so in this case, these 2 forces will cause what? Tensile stress. So the answer is C. But if we take the original problem, which is left lateral fault or left lateral strike fault, okay, so I have the pipe. Let me draw it here. Let me double check something because, and this is a fault, and the fault is left. So if I'm standing here, so the arrow is to my left. I was standing here, the arrow to my left. And if I'm standing here, the arrow to my left, which is the same as this one here. So if you take this force right now, which is along the fault, and resolve it into 2 components. So a force along the 2 components and to solve it into 2 components, one perpendicular and one parallel. So this force is like this. I will one this way and one this way. So it is one this way and one this way. Okay, so one this way. This is very obvious here. Here it is, perpendicular and lateral. So these 2 forces will cause compression. Compression. Because this is a left lateral strike fault, strike slip fault. in my textbook, if you found a typo or a mistake, by the way, please let me know, because as I told you that when we have a new edition, normally could be a typo or a mistake here or there. I will look to this because I saw something be my attention. This is in chapter 15, by the way. Here it is. When we have the fault, as I explained in the class, those who attended the class, you see here it is. This is a pipe and this is a fault. The fault here is a left lateral fault. If I'm standing here, the arrow is to my left. And if I'm standing on the other side of the fault, the direction of the movement of the fault is also to the left, as shown here. So what we did, we resolved this into two components, one along the pipe and one along the perpendicular direction. And I took many cases and I cover this. So tension or compression will be determined after you. The shear is very unique. Shear stress. Shear stress. Shear stress, we learned this in school. If you have two plates in mechanics of materials subjected to two forces equal magnitude opposite direction, P and P, and these two plates are bolted or riveted together with a rivet or a bolt, some kind of connection for connecting these two together. So in this case, we're talking about the shear stress tau is equal P over A, where B is the force and A, what is the area? A, the cross-sectional area of the rivet. Here it is. The rivet will be like this. This is the cross-sectional area. And this area, by the way, is parallel to P. Parallel to P. The area, this area here, is parallel to P. The normal stress is perpendicular, but this is parallel to. So this is the shear stress definition from mechanics of materials perspective. And from seismic point of view, if you do have a pipe and the pipe is crossing, or the fault is almost perpendicular, so this is the fault line. Fault line. It doesn't matter right or left. If let me make it left right now. If I'm standing here, to my left, if I'm standing here is to my left. So two forces equal my opposite direction, and this is almost 90 degrees. This will create shear stress. So the pipe will be fail under the shear stress effect. When the fault is almost normal to or perpendicular to, or the pipe is, so it will be sheared like this, shear it, okay? Two forces like this, two forces in the opposite direction, shear. So the shear stress is occurring or happening for a utility pipe that is crossing a fault at almost 90 degrees normal. It doesn't matter if it's left or right, or right. Left lateral fault or right lateral fault, they were causing the same thing. But if the angle of the pipe is not near normal or near 90, if the pipe is crossing the fault at an angle, small angle, acute angle like this, as I explained it to you, we resolve the force, and from the resolution of the force, we can determine if it's going to be under tension or compression. But under shear, when the pipe is almost at 90 degrees, and I explained this also, let me show it to you one more time. In my book, chapter 15, figure 15-3, here it is. This is the fault line. This is a fault line. And we used right lateral fault in this case. It is a shear type failure. This one here is the left lateral fault. This is the arrow is here, and the arrow is here. So if I'm standing here, my left, so this is a left lateral fault, and this is the right lateral fault. Right. Under this scenario, either left or right, the shear across here, it is right or left, nearly perpendicular to the pipe. So in this case, the pipe will be sheared, and that's why they allow a certain movement, okay, based on the supports, some kind of. But if you look to this figure 15.4 and 15.5, above ground pipe crossing left, and I have another two drawings on the back, I believe, yes. The orientation of the pipe is different. So I use the XY and I try to explain this. I hope this is helping you guys to make sense. Great. Everybody is awake and everybody is healthy, as long as, and I don't know when they are open the locations again, or the sites. They open the sites again for the. Okay, let me pick another problem or so. Here it is, a problem, torsion irregularity. Problem 343. We need to be ready for both, by the way, to the types of problem, the calculations. We need to be ready to calculate the seismic force, the distribution, the overturning moment, all these things. And also we need to be also ready for the conceptual questions. Conceptual questions. So he is telling you that the plan view of a building or a structure is given, where the seismic lateral force 180 kips. He gave a seismic force in the direction shown. Because of this, the building has been drifted. So the original building is like an L shape here. But due to this, the building has been rotated, will create what's known as a drift. And the displacements or drifts at both ends of the structure are 0.35 and 0.82. So I have one end 0.82 feet, and the other one is 0.35 feet. And the question is, what type of irregularity does exist? torsional irregularity, stiffness irregularity soft story, non-parallel system, or extreme torsion. You will find that stiffness is out. Soft story, I will show you why. And non-parallel system is out. The only two answers left, either 1 or 4. Torsion and extreme torsion. Because the building has been rotated. And if you remember the joke, I was telling you that there are 3 actions in a seismic force acting on a structure. Seismic, as you know, is a lateral force. So any seismic lateral force acting on a structure, it will try to do 3 things. So if the building is here, and this is a seismic lateral force, F, so the building may be translated like this. It has been pushed by this force. We'll call this translation. The building has been translated or moved, drifted this way horizontally. The other possibility that the force, the seismic force, might do and this is F, is rotation. It might rotate about this end O here, or this point O here. This is called rotation. And the term overturning moment is coming from OTM, overturning moment. The third possibility is the building is here, and normally we try to use 3D. And Mr. Mansour, he bought a condominium in this building, and he paid a lot of money because there is a window here, ocean view. So this balcony or this opening here, it is ocean view. But because of the seismic force, is causing torsional moment, TM, torsion moment. So this view that was originally toward the ocean, Mr. Mansour, right now facing downtown. Is it going to be happy? No. This is called torsional moment. Torsional moment. So there are 3 actions: translation, rotation, and torsional moment. And we need to examine or design our structures to prevent all these modes of failure. So this torsional moment is going to cause the building to rotate like this. Here it is. You see? Somebody is holding the building from the top and twisted because of this seismic force here. So we have delta 1 and delta 2. And this is horizontal irregularity. Irregularities, there are vertical and the plane irregularities. Irregularities in chapter 6 or chapter 12 of the ESC 7. Irregularities, there are 2 types: horizontal or a plane irregularity, and the other one is called vertical irregularity. And they are total 12, 7 and 5. If we do have a plan view like this is a plan view. Here it is. He said that a plan view. I need you to think immediately about horizontal. Because horizontal irregularities, all of them are a plan view except one. But vertical irregularities, all of them are side views. Side view. Translate into English. Let's go to chapter 6 and see if what I've just said is in agreement with what I presented or not. So I will go to chapter 6 of my book. Maybe if you have other book, maybe they cover it different chapter and cover it differently. But the point is, as long as you understand what is meant by that. So chapter 6, and when we come to irregularities, here we go. I talked about the two types of irregularities as introduction here in this table 6-12. Regular structures versus irregular structures. What is meant by regular? Nice, regular structures have no significant physical discontinuities in the plan. Nice building, you see. Compared to this is a side view. This is a vertical irregularity. Building in and out like this. If you look to the plan view of a building, nice rectangular or square, but you'll find that it has an L shape. It's called re-entrant corner. So there are 7 and 6. They say 12, 6, 7, and 6 is 13. Okay. Oh, yeah, 13. That's correct. Sorry, I said 12. I'm sorry. It seemed that I need to remember how to add 6 plus 7. Okay, so I forgot that. So 6 and 7. So this is a side view. This is a plan view. So the plan horizontal irregularities examine the plan view of the building. So these are the 6 horizontal irregularities. 1A, 1B, 2, 3, 4, 5. One is called torsional irregularity, and the other one is called extreme torsional irregularity. They added this recently. In the past, it used to be 1, 2, 3, 4, 5, but this way they broke it down to 1A and 1B. But it used to be in the previous code. Because as you know that every time there is an earthquake event, scientists and seismologists and engineers, and they sit together and go over the code and see what damage happened due to this earthquake, and if they can modify the code to account for any damage that they were not aware of. And it's a learning process. If you look to the seismic code or codes over the years, they change a lot and they add in a lot and modify a lot. Even after they issue the code, they discover, oh, we found something else. So they issue an errata or supplement or something like that. So which is a learning curve for all of us. But this is a current code that we're going to look. So these are the two that they are mentioned in the problem. So what I did, I took this English, because if you read this torsion irregularity, what does it mean? It means that torsion irregularity is defined to exist when maximum story drift computed including accidental torsion with A sub x is equal 1 at one end of the structure. A transverse to an axis is more than 1.2. The average of the drift at both ends So I'll give you a statement. I took this statement and translated it into English. How? I put it in a form of, here it is. This is the translation. So I have a building and it has been drifted due to this V, delta 1 and delta 2. One smaller than the other. So if delta 2, which is the maximum storage drift, this is the language of the code, at one end is more than 1.2 times the average of the stored drifts at both ends, this is the equation and this is the equation after simplified. The extreme torsion, this is the torsion irregularity, and instead of using 1.2, they are using 1.4. So basically in this problem here, the one is given, I will apply that. I have 0.35 and 0.82. I will say that 0.82, which is the larger one, 0.82, is it greater than 1.2 of the average of the two, 0.35 plus 0.82 or not? So let us put a question mark here, 0.82. So basically you apply the definition of the torsion irregularity. So in this case, it is 0.35, enter, 0.82 plus 0.5 times half, and you multiply this 1.2. So this can be to be 0.70. Let me do it one more time, 0.35, enter, 0.82 plus 0.5 times 1.2 times, it's 0.702. Okay, this is for torsion irregularity. If you look to the extreme torsion, which is the same equation, 0.82, if the 0.82 is greater than 1.4 of delta 1 plus delta 2 divided by 2, which is 0.35 times 0.82 divided by 2. So 0.35 enter, 0.82 plus 0.5 times 1.4 times. So this is 0.82 and this is 0.82. This is 0.8, let me put it at 0.819, by the way. So right now, is 0.82 greater than 0.1.7? Yes. So for sure, the torsion irregularity number 1 exists. But does the extreme exist? This is 0.82, and this is after the around 0.819, which is almost 0.82. So 0.82, in this case, they are equal. So the extreme does not exist. And this is why they select the answer is, this only exists, and the answer is A. Any question about that? We need to make sure that we understand that, how to apply the irregularities equations. or irregularity conditions. Any question about extreme torsion? And be careful, by the way, equal sign or greater than, this must be greater than here. They make it that greater than, a greater than. There is no equal, must be greater. If they are equal, that means that, like in this case, and this, I made it a problem like that, such that it will give you exactly 0.82 and 0.82. So this is not, this does not exist. This side must be greater than this. Make sense? So only one irregularity, which is the torsion irregularity. This way I select the answer A. And again, if you find a typo or a mistake in my book, always I mention this. I know I mentioned more than once, but it will not hurt. I did my best to review all these books. I reviewed it myself and did it myself, and it took years, 30 years. 30 years of teaching resulted in all these books. So at 2 universities, so it takes time, but I am a human. I do mistakes like anybody else, or I do typos like anybody else. So it's not. Make sense? Good, good, good. Everybody is awake and everybody. So since we are on the same page, and this is a very good problem, torsion, because torsion is one of the topics that I found in the past is a little bit. So the problem is 344. It is the same problem, but he told you there is a seismic force of 180 kips is considered. So the V was calculated and it was found to be 180 kips. He's asking what is the torsional moment due to accidental eccentricity only, considering any amplification is most nearly. Amplification, as you remember, there's something called A sub X. It's called torsional amplification factor. Torsional amplification factor or coefficient. Torsional amplification factor. I believe factor. Maybe. I can look at it. Torsional amplification A sub X. Yes, torsion amplification factor, yes. Okay. And the A sub X, by the way, is given by the code as the delta max over delta 1.2 delta average, and this square. And A sub X, it has limits, by the way, between 1 and 3. Torsion amplification factor. And we apply the torsion amplification factor, by the way, to the accidental eccentricity only. Let me remind you, for those who took the class with me, when we are saying that M sub T is equal to the V times E actual plus or minus A sub X times E accidental. This is the equation that we use it in order to calculate the moment. And this is what he's asking you to do. So I need to get A sub X for this problem here. I would be glad to scan this for those who probably don't have my book. I'll be glad to scan this. This way I'm writing somewhere, sometimes here. So A sub X is equal to delta max is 0.82 divided by 1.2 delta average, which is 0.82 plus 0.35 divided by 2. and this quantity will be square. So let me do it and catch my mistakes if I did a mistake. So it is 0.82 enter, 0.35 plus 0.5 times, 1.2 times, invert 0.82 times, and second square. So this came 1.47. So a sub x between 1 and 3, so it's acceptable. So I will use 1.47. So in order to get the torsional moment, due to accidental eccentricity only is the force V, which is 180 kips, times a sub x, which is 1.47, and the plus or minus, don't forget the plus or minus, with the equation as a plus or minus, times the E accidental. What's E accidental is 5%, 0.05, times this dimension, which is 35 plus this, 65, so it is 70, so 100 feet. So if you do this calculation, if we came up with a number, any number in this, did I miss anything? I think I wrote the equation here. Normally I check the equations because, so he is considering this only. So it is V times a plus or minus, in this case a plus or minus, a sub x times E accidental. So plus or minus 160. A sub x, we found it to be 1.47. And the E accidental is 5% of the dimension perpendicular to V, which is 65 feet plus 35 feet. So if we do this math, which is the same as, I wrote it here, by the way, but 1.47 times 0.05 times 100. So let us do this. This is kip, by the way. The answer will be kip feet. Seems that I was singing, so my voice is almost gone. My God. Okay. So 160, 1.47 times. Let me make this. This is like Egyptian 7. Make it a nice 7 here. 160, 1.47 times, 0.05 times, 100 times. Oh, I got something different. So 160, enter. 1.47 times, 0.05 times, 100 times. Oh, I got a very large number. 1176 kip feet. Did I? Okay, 1.47. Yeah, it's correct, I believe. One more time. 1.47 times, 0.05 times, 100 times. Yeah, 1176 kip feet. So if you have 4 answers, 800, 900, 11. Did I pick anything wrong here? 0.82, 0.35. There is something, okay. We're supposed to get very close answer, unless rounding, no. It's unless this is wrong. 0.82, let me do this one more time, of delta average square. So it is 0.35 enter, 0.5 times, 1.2 times, inverse that, 0.82 times, and second square. Oh yeah, this number is not correct. This number is a mistake here. Let me do it. I got 1.36. not 1.47. Sorry, 0.82 enter, 0.35 plus 0.5 times, 1.2 times, invert 0.82 times, and second square. Oh, what I'm doing here? 0.82 enter, 0.35 plus 0.5 times, 1.2 times, invert 1.82 times, second square. No, it came to correct, 1.47. And the 5% of 3565, that's correct. 1.47. So 1.47, 0.05 times, 100 times, 180 times. Okay, let me look to my solution, what I did. Because I got number is a little bit off, because sometimes I change the numbers. 0.82, 0.35, everything, it looks good. Okay, okay, let me look to my solution. Problem number 344, because it's very odd number here. 1170. Oh my God, this is supposed to be 180 kips, not 160. I copy it wrong. Okay, that's why. Okay, so 180. Sorry, you see, it is 180, not 160, my friend. This is my fault. Same that. So it is 180, 1.47 times, and this is 100 times. This is what I got, 1323 kip feet. Again, but does not match any. Let us look to see, unless I change the numbers. 344. This is interesting. 344. Probably I did something. 344. Okay. So it seems to me the 1.36 is the correct one. Let me do it for the a sub x. Why I ended with 1.47? So it is 0.35 enter, 0.82 plus 0.5 times, 1.2 times, and 0.02 times, and square it. No, this number is not correct. 1.36. I use 1.36, but it turned out this number is not correct. It's 1.46. So I will look to this problem again. The method is correct, everything is correct, except the A sub x, which is a torsional amplification factor, it is not calculated right. Seems to me that it is less than 3 because A sub x between 1 and 3, that's good. So it seems to me there is something wrong here with this value here, which is, I will look at it one more time. Yeah, it is 1.36. This number here, one time it comes 1.36, one comes 1.3. Oh my God. Okay, let me listen to one of you, probably some of you, or one of you has, it's 1.36 or 1.46. Let us get, I got 1.36, so you saved my life. Okay, so probably, okay, when I'm probably, because I'm fasting today, so probably the energy is gone. So if it is 1.36, that's correct. So it is 1.2. So it is 1.36. That's good. So the equation is correct, everything. So it is 1.36. I don't know how we get 1.47, but that's fine. It is 180 enter and 1.36 times and 5 times. Bingo. 1244. So it seems to me that, let's go back again. 1244. So I selected answer C. Okay, yes. Yes. So we are. So sorry for that, guys. It seems to me that, forgive me because I wake up at 4 o'clock this morning. So this is not 147, 1.36. Here it is, 1.36. It seems to me that when I'm hungry, I'm not doing very well. 0.82 enter, 135 plus, 0.5 times, 1.2 times. Where's 0.82, 0.82 times, second square. Bingo, okay. So it is. Okay, no doubt, it's 1.36. I did about 5 times. Okay, 1.36. So 1.36. So 180, 1.36 times, 0.05 times, 100 times. So it is 1224 Cape feet. So this is the answer C. Sorry, guys. Oh, okay, good, good. But at least we discovered our mistakes here, or I discovered my mistakes here. Okay, so this is, try to do your best, and I will keep working with you guys. For those who are taking the exam very soon, I don't know how soon it will be, and let me know. I will be glad to set a special session for those who, but come up with the questions, because I need you to come up with questions. Okay, and hopefully this will be after Ramadan, so I will not be fasting, so I will not. Here it is. Okay, 1.36. Okay, so do your best, and I will do my best, and I will make a copy of this when I scan these things and send it to you. So my notes, I will send it to you also. Okay, I have about 6 pages here, and I will make a copy of this for those of you who do not have the book. At least you can see my Egyptian handwriting. And thank you. Let me stop here because I have only one camera left. It will take me to home. So forgive me for that. Okay, thank you very much for coming, and keep doing your best. And let me correct this here right now, because this is 1.4. So even 1.160, I copy 160, 180, copy 160. So this is 1.36. And this here is the 1442. Yes, it is 1224 Cape feet. No problem. Okay, so they are 7 pages. I will send you these 7 pages with all the corrections that we made today. So 7. Okay, and Today is 5/3/20, and this is Seismic workshop. Okay, thank you very much, and appreciate your coming today, and let us do our best to be ready for the exam. And email me if you have any specific question related to the subject, and I will do all my best to help you all the way to the end. These lectures, by the way, will be available. These recordings, this recording will be posted. I think my staff, they are posting on YouTube, maybe, or my homepage. There are some directions on our website. If you go to our website, you will be able to see all these recordings. Try to look at again, and if you disagree with me about something, or you found something that needs to be discussed, I will be glad to do that, to do so. Okay, so let me stop here early, a little bit early, half an hour early, because I think okay, thank you very much. Bye bye.